Okay, hello and welcome to this lecture on gradient echo pulse sequences. This is covering both the material in chapters 20 and 21 in MRI the Basics. Okay, so our goals for this two chapters are revisiting some things we've covered a little bit. For example, what is a gradient echo pulse sequence, but then progressing on to a few new things. What is partial flip angle? What is fat water imaging or the Dixon method, that are building off prior principles that we've introduced, a refresher here in chapter 21 of what is spoiling, but then introduction of a balanced steady state free precession sequence. Okay, so we'll start this with this basic refresher. Again, what is a gradient echo pulse sequence? And gradient echo pulse sequence is simply referring to one of our simplest pulse sequences, applying an RF pulse, then do a frequency encoding gradient. And the part that actually refers to the gradient echo is, if you recall, it's like this point right here. And this is going to be our echo time. It's going to be when our K space is equal to 0. So what that means is that we've refocused the effects of our gradient. And so if you were actually to look at the signal, it might look something like the sketch on the right, where at the time when the effects of the gradients are refocused, actually the signal in fact looks the largest. It looks like an echo. But there's something notable about the sequence in the right here, which instead of showing a 90-degree flip like the example I showed previously on the left, uses an alpha to represent an arbitrary flip angle. And that's one of the key points we're going to talk about here in the gradient echo pulse sequence. Okay, so I'll start off here by illustrating repeated 90-degree pulses, which in a gradient echo sequence, and which we'd use the term before both partial saturation and saturation recovery. That's referring to the same pulse sequence. This is really this repeated set of 90-degree pulses. And just a quick refresher, the magnetization starting along the z-axis gets tipped down, then only the partial saturation means it only partially recovers along the z-axis. We get our signal, xy, and then the next TR, we haven't fully recovered to mz, so we do this repeated pattern. But where because we have incomplete T1 recovery, we have this equation that the signal is proportional to TR over T1 here. And that signal curve, and here are some examples of in the brain or in the head for the expected signal. It's a function of TR for different T1 values. Now, what the partial flip gradient echo refers to is simply the same set of repeated pulses. I guess I've got plenty, but now we're going to use this notation alpha to refer to this as an arbitrary flip angle. Do some data acquisition here, draw on a couple of these. And what's going to happen in this case is we're going to get this partial tip of the magnetization. So start along the z-axis. But then instead of tipping the magnetization all the way into the transverse plane, we only tip it partially into the transverse plane. So we get some reduction in mz and some transverse magnetization signal created with some T2 star decay because we're in a gradient echo sequence. And then usually these are very short TRs. So I'll draw just a very small amount of T1 recovery. And then we'll do another flip, which will, so at this point there's less magnetization, the XY is gone, but we haven't fully recovered back to equilibrium. So we'll get maybe a little smaller signal here. And this will kind of repeat. And we'll explain what happens here, but actually if we did this a few TRs in a row, the magnetization should be steadily decreasing. Okay, so here we're going to zoom in on the first couple of TRs there, figure out how we transition into the steady state. So we have a few of our pulses. I guess I got to draw them a little shorter because they are going to be small flip angles typically, some arbitrary alpha flip. And we're going to start at equilibrium, so that the net magnetization along the z-axis. We'll get some tip down here, and we'll create some transverse magnetization. Now this is going to be a net rotation. So the amplitude here would be whatever z was before times the sine of alpha. And this value right here is going to be, cosine of alpha. Gosh, I'm thinking theta, no, alpha here. So that's this value right here, and this value right here. So it's the trig relationship for this rotation by an arbitrary angle alpha. Then, well, maybe a little hard to see, but there's going to be Ch2 star decay. For now, let's assume that it's 0. And the next TR, we'll refresh on that briefly later. And then there's been some T1 recovery here, but not complete, so we might be at some smaller value. So again, we haven't, up here would be M naught. We haven't reached that yet. We're going to hit the next flip angle, which again is going to tip the magnetization out. We could derive this with the trig relationship. And now we're going even further away from the equilibrium value. And the transverse magnetization is going to follow here as well. And so what I'm trying to illustrate here is that the magnetization is changing TR to TR. But eventually we do transition into a steady state. And once we get there, we can derive what the signal contrast is going to be. So here I'll use some dots here to illustrate. We're just looking at in the middle of the sequence once we've got to the steady state, which can take tens to hundreds of TRs. And what's going to happen in the steady state is that the amount over here that is created by the tip of the RF pulse is going to be equivalent to the amount of T1 recovery that we have within a TR. Okay, so, and then of course we'll get some transverse magnetization from this, but we really, to determine the contrast, we're really going to zero in on MZ. So we're kind of going to call this height here MZ minus. This one as well, MZ minus. And what I've said is the steady state. It means that these two are in fact equal. And then this value here, call this MZ plus. Again, it will be the same between our two different TRs here. I should add that timing on as well. Okay, so now we have actually all the information that we need to determine what the signal contrast is. And the first relationship we need is that the Z magnetization after these RF pulses is going back to that trig relationship, is the Z magnetization before the RF pulse times the cosine of our Greek is just not doing well. Times the cosine of our flip angle, okay, alpha here. And then the other thing we need is our T1 relationship. And so this says that MZ at the end of the T1 recovery interval here is going to be equal to whatever mz was at the beginning of the interval, times e to the minus, now the t is tr, t1, plus m naught, 1 minus e to the minus tr over t1. And if you're confused about where this is coming from, go back and refresh on the tissue contrast where we derived our T1 recovery signal equation. Okay, and then the last piece, so we can actually solve for mz plus okay, or actually usually want to solve for mz minus. Because that's what's going to determine our signal. So our signal is going to be proportional to mxy, and this plus, of course, what's after the RF pulse, which will equal mz minus times the sine theta. And you can go through the math here, determine that the mz minus here is a couple of exponential terms, but the twist here, I'm sorry, I used theta from this equation a lot. I should have kept it consistent. Alpha is that we have a cosine of alpha here term in the denominator. It multiplied by our exponential recovery terms, and you can combine these together and get the signal contrast in this partial flip case. Okay, and so if we were to plot that equation that I just wrote on the last slide for these same example brain tissues, fat, white matter, gray matter, CSF, and some of the images, you'd see signal curves like this. And a couple of interesting things we can point out here. One is that actually in our low flip angles, like this image is down in our low flip angles, you get proton density contrast actually, or proton density weighting. Turns out you end up with a sort of linear relationship. And then you start to accumulate some kind of T1 weighting. And we'll just draw it sort of approximately out here. We're definitely going to have T1 weighting. Another thing I want to point out is, these curves all have a distinctive maximum, and this is going to be the optimal signal if you want to consider just the most signal you can get for a single tissue. So that's about these maximum points of these curves, and that's what's written over here. Is this so-called Ernst angle, named for the person who derived this principle. And you guys have seen that in the homework a little bit as well already. Okay, so now I'm going to move on to the next part of the gradient echo imaging, and here this is a refresher of the chemical shift boundary artifacts. It was covered in the artifacts lecture. And this was this phenomenon that at different echo times, we could get signal cancellation between fat and water. So recall within the same voxel, the transverse magnetization could, due to chemical shift, could actually get fat and water out of phase. If this is not ringing a bell, I'm going to go through this drawing of this again right here. Okay, so let's say we had a voxel here. Some part of it is, let's say this is, water, and Some other part of it is fat. And in this case, actually, I'm not so doesn't need to be so specific, excuse me, to being in the same voxel. Okay, but what we assume is that water is on resonance, so it gets tipped down into the transverse plane. Here's time moving along here, and that the water remains aligned, so it has no net frequency offset, whereas our fat, we said, had some frequency shift due to the chemical shift phenomenon. So at an initial time, and this would be at some echo time equal to 0, it would be in phase with the water. Now I'm going to take a certain time here, choose it such that our fat has rotated by 180 degrees. At the next echo time, and we might call this an out of phase echo. And then actually at some later time, in fact, double that one, once again, fat and water could be in phase. And the idea of how we're going to separate these is utilize this fact that we can put the fat and water in and out of phase of each other. And in fact, they can, just as in the boundary, or similarly to in the chemical shift boundary artifact, this phenomenon causes an artifact when they're in the same voxel. We can also use this phenomenon to create distinct images of fat and water. So sometimes this is called the 2-point Dixon method, in that we're getting 2 points of data. One, a so-called in-phase echo time, as I was illustrating on the last slide, where transverse magnetizations for fat and water are completely aligned. And then we get a so-called out-of-phase data or image, where fat and water are completely opposite phase. And you can see, in fact, in these images, you have the signal cancellation artifact. And then what you can see graphically is that if we add these two images together, then the fat is pointing in opposite directions in the two images, so it'll cancel out and we'll be just left with water. Whereas if we take the difference, now the water pointing in the same direction cancels out and we're left with an image simply of fat. And this can be accomplished with a pulse sequence like shown at the right here. This is a very common and very powerful technique, particularly imaging in the body, where you do have a lot of fat around the organs of interest. Now, practically, turns out to be a little bit of a concern with this. Say, again, might have one voxel where we could get this nice, in and out of phase behavior. Okay, or some region where we had this in and out of phase behavior. Let's say we had in a different region where the difference between these two, or the two voxels or two regions, would be here. We would assume on resonance, or sometimes I use this notation. There's no change on the net magnetic field due to other phenomenon like magnetic susceptibility. But so suppose we have an off resonance voxel where the main magnetic field is not perfect, or we have some magnetic susceptibility, an air tissue interface. What could happen in this voxel is that now even our water, which would be nominally aligned along the x-axis, is actually going to rotate as well. It's going to accumulate some phase because it's not perfectly on resonance. So it might accumulate a little phase over time. The fat is going to accumulate this little bit of extra phase plus something else. And so there's still going to be these so-called in and out of phase times, just like we had before, but we can't simply add and subtract an in and out of phase because of this different angle of the vector. It's just going to screw things up. And this is practical. This is what's going to happen in real imaging scenario. And sort of to describe briefly, the solution for that are sometimes called three-point Dixon methods. The intuitive approach here is that we're going to get 3 different images now, both an in phase and out of phase, and then an extra one, either in phase or out of phase. We can use the 2 that are either in phase or out of phase, wherever we have a double. We can use that to estimate the field map, so this delta B0 term. And then we combine this information, and we can ultimately still separate fat and water. It turns out practically and more efficiently, you can actually do different, you don't have to do exactly in and out of phase. There's these cool techniques. One of the most famous is called the ideal method. And some more clever, very interesting ways that this is done. There are also ways using, for example, iterative methods that assume a spatial smoothness, of the off resonance, which is usually a pretty reasonable assumption. Although you see some issues, and there's some examples here where there's sort of swaps of the fat and water. So the algorithm, because it didn't have the absolute field map, it was trying to estimate it, made these errors here. It's kind of obvious in the next one, and over here, this kidney gets knocked out. Okay, switching gears now, we're going to get into chapter 21. The first thing I want to comment on is the concept of spoiling. And we've pretty much always assumed that the magnetization is spoiled at the end of each TR. And this means we're usually looking at down below what are abbreviated as SPGR or flash sequences. These are spoiled sequences. But there are advantages, particularly SNR, to keeping the magnetization unspoiled at the end of each TR. And I'm going to skip over, the book goes into these middle techniques, GRASP, FISP, SSFP, PISP. But really the one that I think has seen the most use is this bottom case balanced SSFP, sometimes called Fiesta or true FISP sequences that are actually completely unspoiled. So a very interesting sequence. And they have some unique advantages. So the SPGR or flash, and these are their trade names, make this assumption where, say, we have some flip angle like we've been illustrating, say, for the partial flip. So we're going to repeat that flip angle. It has some Z magnetization. It's going to do, that's not even funny. Tip, Z, and we're going to get some transverse magnetization, and we're going to acquire data from this. Now, suppose I often draw this transverse magnetization as it's gone, it's going away very quickly, but suppose, it's actually a very long T2 star relative to the TR. What's going to happen here? And what the assumption of spoiling is that, in here we add one of these techniques. So one option for the gradient spoiling, draw it right next to that, is that we'd insert this big, what we called before, the crusher gradient right there. And that would have the effect of, well, once we're out of this, actually, we've effectively removed the transverse magnetization, and then we'll get some repeated excitation, and things will look the same from TR to TR. There's another trick with this. It's kind of interesting if you want to know more about it. RF spoiling. That's changing the angle of the rotation of the RF pulse that has the same similar effect. Now, the other interesting technique that I want to talk about are so-called balanced SSFP, true FISP, Fiesta sequences, and they have what is called, and I'll illustrate on the next slide, fully balanced gradients. And they lead to this interesting like T2 over T1 weighting. So you can see it has a very advantageous like high contrast for both for fat, but particularly of interest like in cardiac MRI and angiography is the fact that the arterial blood here is much higher signal than, say, most muscle tissue. So like the heart muscle that's around the blood gives this very strong contrast, and because it's very fast and very SNR efficient, that makes it very suitable for cardiac MRI or other areas where you might have some movement. It does have this problem. Major issue is these banding artifacts, which is this. I'll point one out here, this dark line showing up, and this is in the chest wall. And that's not, there is actual probably fat right there, but this is the problem with the pulse sequence. If you, this is a great paper. I've got the DOI listed here, but this describes the technique. And what the balance part means is if you look at the balanced SSFP sequence here, the goal here is that the net gradient area of slice, phase, and read gradients is that the net gradient area is 0, or they're so-called balanced gradients. So really that means there's no phase from the magnetic field gradients when you come to the next TR. And so then you really just have the RF pulses just tipping the magnetization back and forth, and that's what's illustrated in the right, figure 3A. So you start with the magnetization at the open circle along the z-axis, and the way these sequences start, interestingly, is with an alpha over 2 pulse, like this, and then they do a flip the opposite direction of minus alpha. They'll come back here, and then flip with a positive alpha, and so you kind of flip the magnetization back and forth. And then what part B is adding is that, well, as you're doing this, you're kind of going back and forth on this cone. You have T2 decay and T1 recovery that's occurring, and eventually you get into some sort of steady state, as we were talking earlier about in the partial flip case. And part C, I won't elaborate on much more, but this is talking about how to transition into the steady state. So this alpha over 2 pulse, this is a great reference if you're interested in that a little bit more. And this is an interesting set of images I found from article in Radiographics, which is a resource for education, for radiologists in particular, very good for any of us learning MRI, particularly how it's used, showing some differences in the contrast between these, and in the arrows in a couple of these sequences on the left two, it's pointing to T2 star signal loss, but some bright blood signal. On the far right, we see that the really high CSF signal in the balanced SSFP sequence. And the last thing I'd like to touch on from chapter 21 is the idea of magnetization preparation. And in fact, you've already seen a case of this, and inversion recovery is one of those where we do inversion pulse to so-called prepare the magnetization, impart some contrast. In the case of inversion recovery, we're often doing this for annulling CSF or fat suppression, although there are other examples. And the way that these are used actually practically is a little bit different than what I told you before, especially for the case of gradient echo imaging. So let me illustrate this for the inversion recovery case. You'd still start off with a 180-degree pulse. Probably wait some delay time. So if we're to illustrate that, we start on M0, invert the Z magnetization, nothing going on with the transverse magnetization. Might wait for some time, T1 recovery, and no data acquisition. Oops. Going on here. But then, once we get to this point, instead of doing a single 90-degree pulse, we'd actually do a train of small flip angle pulses. And the purpose of this is actually what's going on at the bottom is we can do a bunch of different data acquisitions for a single preparation pulse like this. So we'll get some magnetization, but and so usually we're kind of approximating it with the same relationship for TI and TR, but in reality the behavior of the magnetization is a little more complicated, right? We're going to have some small tips, there may not even be maybe a slightly different signal. I don't know if I can illustrate this very well, but because of what we discussed before about transitioning into the steady state and fast gradient echo and partial flip imaging, there's maybe no real steady state, but it turns out that doesn't matter too much, that you can still get pretty high quality imaging with magnetization preparation and this train of smaller flip angle pulses. Okay, so you made it to the end here. What you should have gotten out from this chapter is a refresher of gradient echo pulse sequences, what a partial flip angle scheme is and what the contrast is from that, and also what is fat water imaging, or the so-called Dixon methods. And then going into chapter 21, refresher of spoiling, and the introduction of the balanced steady state free precession pulse sequence and its contrast. And then also discussed the concept of magnetization preparation, which we've seen before in the form of inversion recovery, but now introduced how it's used with fast gradient echo imaging. Great, thank you for watching.